Ladies and gentlemen, thank you for joining us today. My name is Dr. Fred Osman, and as the Teachers Guild of New South Wales President, I would like to welcome you here today for this online Teach Meet session with Tibor Molnar on learning with STEM, what the world must be like. A quick moment for housekeeping. Please keep your microphones muted during this session to minimise background sounds and interruptions during the presentation. You can also choose to have your camera on or off during the session. You're welcome to use the chat box throughout the session, and I will volunteer to keep track of the chat box so I can feed the questions during the Q&A session to the presenter and come back to your questions at the end. The session will go for an hour and will be recorded so we can have this presentation available for you and other colleagues after the event. Our presenter, Tibor Molnar, studied chemical engineering at the University of New South Wales in the 1960s, but then forged a career in IT and business. Tibor now pursues a wide range of interests from physics and neuroscience to AI and philosophy. An honorary associate of the Department of Philosophy at the University of Sydney, Tibor teaches philosophy and science at the University Centre for Continuing Education and the WEA. Thank you, Tibor, and the session is now all yours.
Good, thank you, Fred. Let me turn myself on here. I need to do that. And then I need to do that. And that. Good. I hope that's all now visible. Okay, well, can you all see that? Excellent. Okay. Well, welcome everyone to this short talk on international maritime signalling, or perhaps if you prefer, you might like to hear me talk about STEM. This talk starts with a mandatory health warning. I have to warn you that it may contain traces of nuts. This is the outline of my talk. I hope it'll have a beginning and an end. What happens in the middle is going to be a mystery to all of us, particularly in these times when these talks are run on Zoom. The last time I ran one of these talks, I had a power failure and the whole thing died in the middle. So anything can happen. To set the scene, let me start with a little bit of history. The scientific revolution started in Europe in the 16th and 17th centuries. Perhaps we could say it started with Copernicus when he published on his deathbed, when he published on the revolutions of the heavenly spheres. And it took off remarkably quickly. There was Francis Bacon in 1620. There was Galileo in 1632. There was Newton in 1687. And in fact, by the time of Newton, the scientific revolution was already very well established. By 1840, William Whewell, an English polymath and philosopher and an Anglican priest and also master of Trinity College at Cambridge, coined the word scientist. That was in 1833. Now, this scientific revolution, with its focus on experimentation, fairly rapidly gave rise to the steam revolution. Steam revolution followed in the 18th and 19th centuries. In the year 1698, or in fact in 1702, the Savory steam pump was put to work pumping water out of coal mines. And that was probably the first time that steam was used to actually do work. There were other gadgets that played with steam, but none of them actually produced any useful work. And that also developed very rapidly. We had the Newcomen atmospheric engine in 1712. Boulton and Watt came about 50 years later, Trevithick in 1801, and then the famous Stephenson locomotion in 1825, which looked a little bit like this. It was called Locomotion Number 1, and it's aptly named because on September 27 in 1825, it opened the world's first public passenger railway in the UK. The original of this machine is still alive. It's in the Darlington Railway Centre and Museum in County Durham in northern England. Of course, by 1880, the steam revolution had become this. And it's probably easy to see how in the second half of that century it became known as the Industrial Revolution. It was quite revolting in its own way. This Industrial Revolution was well, it was mechanization by steam power, basically. The steam engines were in factories, they were absolutely everywhere. But it was not an unqualified success. It brought about a rebellion by the English textile workers. You might remember the Luddites. It brought about a rebellion by the English agricultural workers, the swing riots as they were known. And in fact, it gave rise to Marxism and communism. And we've been enjoying the fruits of that kind of thing throughout the 20th century. Communism looked like a really good idea. And it's easy to see why when this is what was going on. Nevertheless, fueled by the prosperity that was generated by exactly this kind of industrialization, this led to what we now know as the scientific age. And the scientific age was rapid developments in chemistry, every aspect of chemistry. Every man who had a shed was playing chemistry in his backyard. It did wonderful work in physics. We developed everything from electricity to metallurgy. In fact, we did lots of work in material science, and by the 20th century, of course, even quantum mechanics. In biology, we had Darwin's evolution. We had fabulous developments in genetics, and now today in the health sciences, and even geology. We developed plate tectonics, and now we're really good at forecasting the weather. We can tell what the weather's going to be almost a week in advance. But this scientific age was not entirely motivated by pure scientific curiosity. It was mostly about warmongering, fame and fortune, and the pursuit of business opportunities, of course. And again, it's little surprise then that it rapidly gave rise to what we now know as the technological age. Now, technology has affected every aspect of human existence. There's none of us who don't enjoy the fruits of technology, even in the poorest developing world. And with the advent of big computers and big data, we're now well and truly in, well, I guess you'd have to call it the information age. It's all a bit like 1984 out there. Automation and big data just about run our entire lives. And at the end of this current epoch, what comes next is going to be the Garb age. And I'm only half joking. Today, the whole world is up to its armpits, not only in science and technology, but also in rubbish. The global rubbish that we generate is over 2 billion tonnes per year. And we Australians should be rightly proud. We contribute our fair share. We contribute about 67 million tonnes, or 2.5 tonnes per person per year. And we have a lot of rubbish to look forward to. The global rubbish is expected to almost double to about 3.4 billion tonnes. So it's very exciting. Now, the history of the past 500 years, it seems very Anglo-Eurocentric. I know start in Europe and in the UK. But it is in this historical context that I'd like to talk to you about steam. Now, but not about steam engines. I've done enough of that. I'd like to talk to you about a different kind of steam, about science, technology, engineering, arts, and maths. So what is steam? Well, I suppose it's science, which includes physics, chemistry, biology, geology, astronomy, you name it. It's technology, it's machines, systems, processes, including electronics and robotics and so on. It's engineering, it's mechanical, hydraulic, electrical, aeronautical, it's all the things that we know how to do. The arts, of course, include the humanities, the fine arts, and the social sciences. And mathematics is everything from logic and algebra and calculus down to complex systems and computing. So but as you can see from this list, STEAM covers everything. There's nothing that one can study in a school or university that doesn't fall into one of these categories. But then here's the question: if everything is a STEAM subject, then what does it mean to be a STEAM subject? If the term doesn't distinguish anything, then calling something a STEAM subject is meaningless. It's just saying it's a subject. So I think we need a tighter definition. Let me make it simpler. Let me try and summarize these descriptions, these definitions, and see if I can make some sense of what STEAM is. Science is working things out. Technology is working out how to make things. Engineering is making them. The arts, I think, is expressing how we think and feel about these things. And mathematics is a tool for working things out. It's as simple as I can make it. Now, one thing stands out, and that is that the arts is different to the other four. The others are about the world, the arts are about ourselves. The reason it's included in STEAM is historical. In the 20th century, the emphasis has been on science and technology, and the arts have largely been neglected. They've been undervalued, underfunded. I mean, after all, the arts got a $100 million opera house, but they didn't get a $10 billion grant to build a 27-kilometre underground art gallery in Geneva. So unsurprisingly, the arts folk didn't want to be left out. They insisted got included here, and now we have this politically correct, but relatively meaningless term called STEAM. Now, please don't misunderstand me. The arts are important. They motivate us and direct what we ought and ought not to do. The arts shouldn't be ignored and neglected. I just don't think they belong in this group with the other four of these disciplines. So for the purposes of this talk, I propose to set the arts aside and focus on STEM rather than STEAM. Now, STEM is the study then of the natural physical world, of what there is, of what we can know about it, and what we can do with it. And in this talk, what I'd like to do is explore what makes STEM special and what sets STEM apart from everything else and what sets it apart from the arts. So let me tell you about STEM. Well, we can ask, what is STEM and what is it for? It's, I think, an interdisciplinary approach to learning to deal with the real world. Students study STEM, but in their later careers, they actually don't do STEM. They do chemistry, or they do physics, or they do electrical engineering, and so on. So STEM is something that we study, but we don't actually practice, at least not directly as STEM. Like the steam engines, STEM requires inputs and produces outputs. STEM has that in common with steam engines. It produces tangible outputs, which are solutions to real human problems. It has a multi-level interdisciplinary approach to doing this. It's a very useful thing and it's highly productive. It also has intangible outputs. They're explanations of how the world works. And we do that just because we're curious. I mean, we study cosmology and archaeology, not because they're useful outputs, but just because we want to know what was going on. And to do these things, to produce these things, we need some tangible inputs. We have to put in time, effort, money, resources, education, and lots of empirical and historical data, what we might call experience. But that's not all. There's something else that STEM requires, which are intangible inputs. All the concepts and ideas, the foundational principles, formal logic, critical thinking, and all the tools for analyzing and understanding and explaining things. And yet this is the stuff that no one talks about. I think this is primary. Without them, science, technology, or engineering are just not possible. And yet no one talks about it. Most schools don't teach subjects like metaphysics, formal logic, or epistemology. So I think this is the area that I want to explore most of all. And I want to describe the intangible inputs and their essential role in STEM. This is the important stuff here, at least for me. So let me start by defining what we mean by science. I think this is something that everyone talks about science, but I've yet to find people defining it very clearly. It's very easy to define what science is not. And this is an example. This is what it's not. Defining what it is much harder, but I think we can say at least this much. Science is the quest to answer just one question, and that is, what must the world be like in order that it produce the phenomena that we observe? So in other words, science is the business of working out what's going on in the world around us. I think it's as simple as that. Hard to answer, but it's a simple question. Now, but there's one difference, interesting difference between science and technology. If science is about working out what's going on and how things work, then it's a quest for understanding. It's a quest for understanding without necessarily wishing to change anything. We want to know what goes on. We don't necessarily want to fiddle with it. By contrast, technology is the opposite. It's about working out what to do and how to do it. And that is a quest for change without necessarily wishing to understand anything. Consider the examples at the bottom of the slide. We study cosmology and astronomy and so on because we want to understand the world, but we're not going to change astronomy by understanding it. But by technology, we do data encryption and organ transplants and drug therapies. And if they work, we use them, even if we don't know how they work. So understanding them is not the primary step, but in fact, changing the world is. So science and technology have a relationship, have almost a cause and effect relationship between them. And I think that difference is worth noting. And typically, this is how we go about doing them all. We start by detecting what's going on in the world. We get our Geiger counters and our cameras and our telescopes, and we start making observations. Then we think about these observations and we try and fiddle with the world and see if we can change things and then see what happens, and we detect them, and round around the circle we go. And we go around many, many times, and along the way we accumulate some knowledge, and if we're really lucky, some technology falls out. And then something interesting happens. What happens is we then put that technology to good use, we put it back into our actions, and we up the ante and make our scientific inquiries more clever by using technological aids. We now have fantastic machinery and research equipment to help us do our scientific work. Now, this diagram is just a cartoon, but it actually accommodates everything we want to say about STEM. Science is everything that goes on in here. It's characterized by this bit. Technology is this bit. Engineering is that bit. Notice the double arrow. Engineering is putting that technology back into practice. And mathematics is just one of the bits about thinking. So while we're here, let me also define what I think thinking is. I think we need to understand what that is. What exactly is thinking? Surprisingly, it's actually not easy to say. Take a moment and think about it. Can you define what thinking is? I've read lots of very long philosophical papers on what thinking is, but no one's been able to give me a really good, succinct definition. Perhaps we can just say it's what goes on in here. That sounds reasonable, but that doesn't advance the argument very far. So I've made up a definition. I had a go because I couldn't find any good definitions anywhere else, and I said this. I said thinking is the product of 4 interlinked processes. They are the intentional manipulation of meaningful symbolic representations. Now that's a bit of a mouthful, So let's read it backwards. You start with symbolic representations. You render them meaningful by ascribing meaning to them, and then you manipulate them intentionally. And that starts to sound a little bit like what thinking is. So thinking is a kind of systematic computation. And it's interesting that these four processes actually come apart. When we're dreaming, we suspend intentionality and purpose, but we still do the other three. When we do brainstorming in a meeting, we suspend meaning. We write down all sorts of things just because we're brainstorming, and when we add the meaning later. So you can actually do different parts of this separately. And of course, thinking can take place in any suitably equipped computer. All you need is a computer with working memory, long-term memory, counters, accumulators, all the bits and parts that a computer has. Plus you need one more thing which computers don't yet have, which is feedback-driven multi-layer networks. When computers get those, and we're now in the process of building them, quantum computing may help in this regard, then computers will become self-conscious and intelligent, but not without them. And of course, thinking happens here. This is the IBM Blue Gene Sequoia. Well, for those of you who are interested, it runs at something like 140 petaflops. It's an incredibly powerful machine. It's over 1 million times faster than Deep Blue, which beat Garry Kasparov at chess. And it happens here. This is the MicroWolf. This is something you can buy in kit form. It's a little supercomputer. Even that can beat Garry Kasparov at chess. And then sometimes thinking happens even in here, and some of those can beat Garry Kasparov at chess as well. So the architecture, of course, in these three machines is very different. But looking macroscopically from the outside, the kind of thinking they do is very much the same, and it's possible to model them in much the same way. Now, critical thinking then is a particular rigorous and disciplined kind of thinking. It's not different thinking, it's just more constrained and more controlled. It involves taking ideas and thoughts and observations and pulling them apart, analyzing each part, assessing it for accuracy and consistency and validity. It's checking the logic of thinking and not just freewheeling as we might do when we think in every day. And then what you do is carefully and systematically reassemble those thoughts, because now you know not only what you're thinking, but you know what it entails, you know what it implies, you know what it means. You've got a much deeper understanding. In fact, critical thinking, I think, is the only path to real understanding. And of course, it has universal application. It applies to anything at all that it is possible to think. Now, to be critical, thinking must be conducted within a strict formal conceptual framework defined by some coherent set of foundational principles. And here they are. We have axioms and rules of formal logic. We have principles of meaning, of semantics. We have principles of argumentation, so-called propositional calculus. And we have principles of value and worth, which fall under the rubric of ethics. And these, I would argue, set the gold standard in right reasoning. That this is what it means to reason things and to think critically. From these principles, plus a number of other bits like the axioms of spatial and temporal extension, Leibniz's principle of causation, Buridan's principle of equipoise, principle of least action, and lots of other critical thinking, we can actually construct our entire understanding of the physical world. That's how we do it. These are the bits we need, and out of these bits, we construct STEM, science, engineering. Everything that we do comes out of this kind of understanding. So, but here's the problem. Defining STEM as science, technology, engineering, and maths, as I did on this flowchart, leaves something out. There's something missing here. There's nothing to guide us, in this diagram at least, as to how to interpret our observations, how to relate observations to each other, how to construct theories, how to check that our theories are correct. What's missing is the methodology, the guidelines or rules that define what we must do at each step of our scientific and technological inquiries. So let's look at this methodology. How does that work? Well, where do we need it? I think we need, first of all, some rules for how to apprehend and observe the world. These are guidelines for delineating images, for recognizing patterns, for pattern matching, curve fitting, and so on. Physicists and chemists will know what some of these things are. We also need some rules for logic and reasoning. These will guide us on how to think. Then we need rules of evidence and validity and truth, and rules for ways of knowing, all that propositional calculus stuff. And that will help us distill out of our thinking the facts that we learn. And then we need a set of rules for iteratively updating our rules, for fixing our errors, for adding features, enhancing our rules to improve the way we go about doing our science. And I would argue then that it is these features, it is these rules that make science scientific. Or we might say it's these rules that make STEM STEMific. Only if these rules are clearly defined and strictly followed can we make sense of the world. Very few scientific errors occur over here. They don't occur in the laboratory. And when they do, they're usually soon detected and corrected. Most of the scientific errors occur here. They arise from the inconsistent application of these formal rules of how we should go about doing things. And then there's other errors which occur here when we incorrectly update our rules and we change our rules without complete regard for how we should go about updating them from the knowledge that we've learned. So these errors don't occur in laboratories, they also occur inside people's heads. So most of the mistakes are theoretical mistakes, they're conceptual mistakes rather than physical ones. And here are some examples. Here's an example from Cambridge philosopher Gertrude Anscombe. She writes in her book, An Introduction to Wittgenstein's Tractatus, she says, Wittgenstein once greeted me with the question, why do people say that it was natural to think that the sun went around the earth rather than the earth turned on its axis? To which Gertrude Anscombe replied, I suppose because as if the sun went around the earth. And well, he asked, what would it have looked like if it had looked as if the earth turned on its axis? Now, that's a fair question. Here the problem is that applying the rules of observation, we applied them too narrowly. We overlooked equivalent alternatives, we jumped to the wrong conclusion. We had a 50-50 chance of guessing right, I suppose. This oversight is a very common error. As Donald Hoffman famously said, we must take our observations seriously, but we must not take them too literally. You can have a look at his 2005 TED Talk, it's quite entertaining. Here's another example. You may be familiar with this. This is the famous Monty Hall problem. There are 3 doors, and behind one door there's a pot of gold. And we are invited to choose a door. Suppose I choose the left door. The probability that I guessed correctly is obviously 1 in 3. But then what happens is Monty opens the right door, revealing that the pot of gold is not there. Now the question is, what is the probability that the gold is behind the left door? Is it still 1 in 3, or is it now 1 in 2? In other words, it's either door 1 or door 2. The answer, the probability or our expectation, depends on how we update our knowledge with the additional information that the gold is not behind the 3rd door. Most people think the probability is now 1/2. The gold is either behind one door or the next. And yet, 2/3 of the time, the gold is actually behind the door we did not choose. To understand why, we don't need to do STEM. You can't do experiments in science or mathematics. These can't help us. These are conceptual problems. What we need is better logical thinking, better critical thinking, and not more STEM. So this is where we need the underlying rule updating methodology. We need to be familiar with that so that we can avoid these kinds of problems. And here's where the problem occurred, right? Some experiences provide no new evidence, so we shouldn't have updated our rules of evidence and validity and so on from the information that the third door did not have the pot of gold. This is all Bayesian conditional probabilities, but it's interesting to see how many people don't know this. And of course, they all went to school and they all learned science and maths and they all don't know this. So the education system is not teaching them these kinds of skills. So these rules and their proper application are what I would regard as the scientific method. And I think that as teachers, we should be paying more specific attention to these rules. For although they are distilled and abstracted out of the practice of STEM subjects, which we do teach, students are not particularly skilled at that kind of abstraction, and practical STEM exercises often don't do it for them. I think we need to spell these out. I think we need to teach these rules specifically and not just by implication from the kinds of subjects that we do teach. So let's have a closer look at the scientific method. I think you'll be familiar with this. You should all be familiar with this. The scientific method, of course, is not over there. It's not in the science that we do. The scientific method is here. These are the foundation elements of everything STEM, and getting here from over there is a non-trivial task. It's been something the philosophers have been doing for 400 years. The rules are not entirely intuitive, and again, I think we should be teaching them actively and specifically. As Carl Sagan said, science is more than a body of knowledge, it's actually a way of thinking. So the scientific method then defines a methodology for how good science is done. And it's been developed over about 400 years, from Francis Bacon to Karl Popper and beyond. We're still updating it even today. I mean, the history is wide. It goes from Aristotle to Bacon to Descartes to Newton to Hume. The list is endless. And it goes something like this. This is the scientific method. Again, I'm sure you're familiar with it, so I'll fly through it. You start with a problem that you might want to answer. You hypothesize based on your accepted theories or what you already know. You come up with some suggestion on what the answer might be. You then make a testable prediction, which you conduct an experiment to test, and you analyze the results. Then you say, is it falsified? Am I wrong? And then you ask, can it be replicated? And if it can, well, then you replicate it again until such time that it has been replicated, in which case you go back to your hypothesis. Now, but remember, you've replicated the experiment and it turned out that it falsified your hypothesis. So your hypothesis is now wrong. This is where the trick is. Now what has to happen is you have to make a decision. Do you accept the evidence and change your accepted theories, or do you rely on your accepted theories and change your hypothesis? This is where the interesting work happens, and that's the area that we need to explore with critical thinking and with our scientific, with STEM, with our thinking, our underlying thinking. That's where the hard part that's where the science meets the gravel. On the other side, if the analysis confirms our hypothesis, again, we check to see if it's replicated, then we check to see if it's consistent with all our accepted theories, and if it's not, we've got the same problem. Do we change our hypothesis, or do we change our accepted theories? This is known as the Duhem-Quine thesis and Duhem-Quine problem, and it's well known to philosophers and probably to many scientists as well. If it works, if it's consistent, then of course we update our accepted theories, we incorporate the hypothesis and go on to the next question. And then everything's fine. But note that there's no check for truth in all this. The only thing that we can do is we can just check our results against our accepted theories. There's no, science cannot discover what is true and neither can maths for that reason. Mathematics can only prove validity and not truth. They're not the same thing. There's no check for truth. All we can do is come up with a coherent model. Whether something is true or not is again a question which cannot be answered in a laboratory. You cannot test for truth in a laboratory. You cannot do science to find out whether something is actually true. But even familiarity with the scientific method is not enough. There's still something missing. And I would argue that that something is what we might call scientific literacy. So let me explore that a little bit. Not knowing science and maths is easily fixed. We teach that in school. Not understanding science is relatively easily fixed with a little careful explanation. Healthy skepticism about scientific claims is also fine. I think we all welcome informed discussion, a debate, a healthy debate about science. Everything's up for grabs. But not being able to think scientifically, I think that's a different matter entirely. That's something that you can't handle easily. And I would argue that that problem is scientific illiteracy. Now, scientific illiteracy is not only bad form, but it's also dangerous. Don't forget, people who are scientifically illiterate get to vote, and they get to vote for the funding that scientists get to do their research. Many so-called science skeptics, climate change deniers and anti-vaxxers, for example, they're not skeptical, they're scientifically illiterate. They actually don't know that what they're saying is incorrect. So I think that scientific illiteracy is a problem, and that's what we need to fix with STEM. I think that's where STEM comes in. John Miller at the University of Michigan defines scientific literacy as follows. He says, being able to understand 2/3 of the scientific concepts and terms typically found in the New York Times weekly science column and in an episode of Nova on PBS. Now that's not a very high bar. And yet in 2016, 28% of American adults were scientifically literate. 72% were not. They failed to understand 2/3 of what goes on inside the New York Times weekly science column. Now, the literacy rate, of course, varies by education. If you have no high school education at all, then only 7% of that cohort will be scientifically literate. But even graduates and people with professional degrees, 62% of them are scientifically literate. But take pause. That means that 38% of university graduates are not scientifically literate. They don't know how to read the New York Times weekly science column. Sadly, we shouldn't be too smug. The rates in Australia are very similar. And I think this is a problem. This is what we need to address. And we don't need to make everybody into scientists, but we need to raise the scientific literacy of the population. So, scientific literacy is what we call metaphysics. It's a thinking that lies behind the science. It's where science starts. Without scientific thinking, there can be no scientific understanding. And this is why STEM is more than just science, technology, engineering, and maths. I think STEM has to include scientific literacy. So let me look deeper into these rules. The rules of detection, apprehension, observation. Let's have a look and see what they are. Well, we have to make certain assumptions, different assumptions about what we mean by existence, what we mean by reality, and these will lead to different, dare I say it, ontological positions, different philosophical positions. Become an extreme skeptic and think there's no reality because nothing at all exists. You can be a solipsist like Rene Descartes and think only yourself and your thoughts exist and everything else is a figment of your imagination. You can be an idealist, a materialist, a monist, a dualist, a physicalist. There's a lot more. There's a lot of different views you can take. And the interesting thing is these positions, these assumptions you make determine how you interpret what you observe. So you take your baggage into the laboratory when you do your science and you interpret your experiments and you interpret your observations according to your preconceived ideas about what you think of existence and reality and so on. So we need to understand what those assumptions are, and I think that's something that's worthy of discussion for people who are budding scientists. Now, even among scientists, there are materialists and immaterialists and dualists and physicalists. They're all there. And they're all going to come up with different scientific theories, which, depending on our own view, we interpret or understand in very different ways. As far as logic and reasoning is concerned, there's a whole lot of stuff there as well. Formal logic is axiom-based and it's rule-governed. It's a way of thinking about things rather than of them. It's a universal system of symbolic representation. It's a grammar for manipulating them. It's rules for valid deductive inference. There's a lot of rules in there, and they are fundamental to set theory, all of mathematics, and just about everything else. And they're essential for making sense of anything at all. Making sense is, in fact, processing things logically. So these rules determine how we think. If we're not good at these rules, and many people are not, even many scientists are not. I can give you evidence, I will in a moment, I'll give you some examples. If you are not good at these rules, then you will not be able to think clearly about your science. And the rules for evidence and validity, well, you need those for your knowledge. Again, there are different assumptions about what and how we know, and these lead to different epistemic positions that people assume even before they claim to know things. There are nihilists who think nothing can be known. There are skeptics who think nothing can be known with certainty. There are scholastics who think that you need to find out the answers to questions and that knowledge comes from rigorous conceptual analysis. And there are idealists, phenomenalists, existentialists, structuralists, and so on. Again, there are many positions. Some of these positions contradict or are inconsistent with others. Again, even among scientists, there are skeptics and idealists and phenomenalists and post-structuralists. They're all human too. And again, they come up with very different scientific theories depending on their particular bias or their particular preconceived epistemic position. And these, depending on our own view, we interpret or understand in very different ways. This is why the debate rages on. This is why there's no consensus in science, despite the fact that everyone thinks there is. So these views determine the kinds of theories we can construct. Now, these rules have technical names. The theories of reality and existence are called ontology. These rules are called logic. And these rules are called epistemology. And unsurprisingly, they are the province of analytic philosophy. And there are people like me who spend an awful lot of time studying them. Analytic philosophy is the science of making sense. Now, it's interesting, STEM doesn't have making sense as one of its components. And I think it needs that. I think this is what's missing. Analytic philosophy, or if you like, making sense, is not directly involved with doing science, but it is indispensable for understanding science. As Fiona Cowie describes it, analytic philosophy is all about bullshit detection. And she's an Australian, so she adds, we Australians are pretty good at it. But we're not that good, and we're not that much better than the Americans. So to make sense of things then, we need first to understand some basic foundational concepts. This is theories of existence. We need to know what we mean when we say things change, what we mean when we say something is an object in the world, what we need to understand, physicality and complexity and so on. We need to understand what it means to make an observation. What makes something detectable or observable? How do we identify what we detected or what we observed? What is the role of the observer? We need to explore the meaning of description and explanation. How do we translate our experiences, our observations into formal language? Then we need to apply logic to manipulate these concepts and compare it and contrast it with others. And then we need to build knowledge by categorization, classification, and by relating concepts. So there's a lot of work that has to be done at the office, so to speak, after you've done your scientific experiment and before you write up your paper for publication. And understanding these concepts is what it means to be scientifically literate. This is where I think the business starts. This is where the rubber hits the road. Learning to do science is not the same as learning to understand science. Without scientific literacy, without an appreciation of what science means and how it gains its legitimacy, learning scientific facts is just an exercise in memorizing. It's there's got nothing to do with understanding. It's just this happened and then that happened and the other thing happened. So scientific facts on their own are not, in fact, informative. To understand them is what really matters. So scientific literacy, of course, is indispensable for scientists. They need it to understand and to explain to us what their experiments and findings tell us about the physical world. Now, it's true, scientists acquire some of this scientific literacy as they learn their craft. When they go through university doing their science, they will become scientifically literate. But there is abundant evidence to suggest that they too could do better. They don't learn enough scientific literacy because you don't learn it by osmosis. It has to be specifically taught. Scientists are often less than clear in communicating their findings, especially in the popular science books aimed at the general public and school students. So it's no wonder we're confused. Here are some shining examples. I've got a few here to show you about the kinds of things they say. Here's Max Planck, the father of quantum mechanics, Nobel Prize winner and all. He comes out and says, there is no matter as such. All matter originates and exists only by virtue of the existence of a conscious and intelligent spirit. This spirit is the matrix of all matter. Okay, so in other words, consciousness, whatever that is, conjures up the material universe. He won't be the first person to have said that. There were quite a few theologians before him who thought that's exactly how it went. The question is, how can this be? What does it mean exactly? How do you get matter out of somebody's thoughts? How do you conjure up a material world? Making sense of this idea is again a scientific literacy question. It's not a physical, scientific, or so-called STEM question. Werner Heisenberg, another Nobel Prize winning physicist, he came out and said in this book, the idea of an objective real world is actually impossible. Now, if that's true, then what's science about? If there's no physical world out there, then what is the science? What is science supposed to be about? Does this make sense? How can a real world be impossible? Sure, maybe the real world we think is the real world. Maybe how we think about it is impossible. Maybe we've got it wrong. But something must be real. The real world has to be possible somehow. And this is another philosophical question, not a question you can resolve in a laboratory. The hypothesis making that we have to do has to come first. And this idea goes back to the ancient Greeks. Anton Zeilinger says the distinction between reality and our knowledge of reality, in other words, between reality and information, cannot be made. Now, this is another interesting question. What does it mean to say that the world, the real world, and what we know about the real world is indistinguishable? Is the world made of what we know, or is reality, is our knowledge part of reality? This has to be sorted out. And I'm happy to ask the question, why can't this distinction be drawn? Do we really live in a what you see is what there is kind of world? This is also not a STEM question where STEM is just science, technology, engineering, and maths. Max Tegmark, in his book, argues that our physical world is not only described by mathematics, but that it is actually made of mathematics. Well, again, it makes me wonder, can anything be made of mathematics? I understand that physics is made of mathematics, but the physical world itself can't be. It's not. As the saying goes, the map is not the territory. The map is made of paper, but the physical territory that it depicts is not made of paper. And perhaps this may be the source of Tegmark's error. It's rather sloppy talk, but you can't take him literally. It's hard to know exactly what he means when he says the world is made of mathematics, and he thinks that's a unique argument. Now, students of STEM need to learn how to answer these questions. But again, none of STEM is actually equipped to answer it. So this too, I would argue, is not a simple STEM question. Then there's Carlo Rovelli. A continuous trajectory towards the future returns to the originating event to where it began. In other words, time goes round in circles. This is a view not held by anyone since the ancient Greeks in 400 BC. So again, we can ask, how is this possible? Can time go around in circles? What is time? It's a fantastic debate currently going on at the Perimeter Institute in Canada. They're arguing about what time is. They're not sure either. So this is, I think, a very interesting question, and it's a way of engaging students in trying to understand what their assumptions are before they try and make sense of the world. So last example, I won't labor the point. In a different universe, Robert Laughlin, yet another Nobel laureate, says quantum mechanical matter consists of waves of nothing. Now I have a question. What is a wave of nothing? Is this a science question? Can you do an experiment to find out what a wave of nothing is? I don't think so. This is actually a trick question. It's a trick question, but we know the answer. I think I know what Laughlin means. He didn't say it, but this is how it goes. Let me show you what a wave of nothing is. Before I start, here's a frame with 15 independent pendulums. They're not like a Newton's cradle. They don't swing from left to right. They actually swing forward and back. They are of different lengths, as you can see, and that means that each pendulum will have a different oscillating period. Now, let me ask a simple question. You all see, you observe these 15 pendulums and the balls. Are we justified in believing that they exist? Make a note of your answer for later, okay? Answer yes or no to whether or not you think these pendulums and balls exist. Now, watch what happens. Oops, no, don't watch what happens. I've got to push this button. Okay, so now ask yourself the next question. Do these wavy patterns exist? Are they really there? You all saw them. We all observed the pretty wavy patterns and how there were 3 or 4 interwoven chains of little balls and so on. But were they really there? Again, you have to answer yes or no. So here's the question. Is it reasonable to believe that these waves exist just because we observe them? The same as we previously said, the pendulums exist because we observe those. Or are these waves some kind of apparition? Now, these waves are what Laughlin regards as waves of nothing, because there's in fact nothing in the pendulums, nothing that waves in this intricate way. All the waves are really just epiphenomenal. They appear because you're seeing 15 pendulums do different things down behind what you see. But here at the front level where you see those waves, there's nothing there. So they are waves of nothing. what Laughlin does is he just ignores or he neglects to talk about the things that are doing the swinging and the oscillating in the background. And he talks about the wave as being a wave, an entity in its own right, and therefore a wave of nothing. So that there's something going on is an empirical matter, but what that something is cannot be determined empirically by experiment. You can see things going on, but that doesn't mean that's exactly what's going on. This is also not a scientific question. If you do science and you see what's going on, you don't get to see what goes on behind what's going on. Incidentally, this demo comes from Harvard University, and on their website, according to the guys who built it, the mathematical description of this wave pattern is the same as that of wave packet revival in quantum mechanics, which kind of tells you what quantum mechanics is about. It's about these apparent epiphenomenal waves and not about the real balls and pendulums behind them. So the question then is, if these patterns are observed, is it reasonable to believe that they exist? Well, Robert Laughlin justifies this by saying physics maintains a time-honored tradition of making no distinction between observable things and non-existent ones. So for him, the pendulums don't exist because he only observed the waves. And we also do this. It's true. Physics does it, and we do it too. For example, unicorns have not been observed, and we happily accept that they don't exist. But then what about dark matter or dark energy or the strings in string theory? They haven't been observed, and yet we think they do exist. So here's a question. Is it reasonable to suppose that something is non-existent just because it has not been observed? I don't think the answer is yes. Perhaps we need Fiona Cowan to come along and do a little bullshit detection. But here's the reverse question. Is it reasonable to suppose that something is existent when it is observed? This is the Immaculate Confection, so named by Mother Teresa, whose image was found in a cinnamon bun in a coffee house in Nashville, Tennessee in 1996. It caused quite a stir. The shop did an enormous amount of business afterwards trying to replicate Mother Teresa cinnamon buns. Now, is it reasonable to suppose that this apparition is real? Well, of course it's not. The relationship between observation and existence is not a straightforward one. And it's not a distinction we can learn to draw by doing science or statistics or mathematics or technology. Observation alone is not necessary and sufficient condition for existence. Just think of aliens and mirages. Here's another example. These are electron probability density distributions. These are the patterns that electron densities form around atoms, okay? In 3 dimensions, these patterns describe precisely the probability of finding electrons around atoms. Well, have a look at this experiment. You may all be familiar with Chladni plates. Okay, and so we can reproduce these patterns. In 3 dimensions, these patterns are called spherical harmonics. And they are exactly the mathematics and exactly the patterns that describe the probability distributions of electrons orbiting around atoms. So this says something about what electrons are doing around atoms. Now, the question is, are these orbits real? Or are they really just patterns of behavior as we've seen here on Cladni plates? This demo also comes from Harvard University. All right, so electron probability density distributions caused quite a bit of, we had quite a bit of fun with those, we caused quite a stir. J.J. Thomson was awarded the Nobel Prize in Physics in 1906 for showing that electrons are particles. His son George was awarded the Nobel Prize in Physics in 1937 for showing that electrons are waves. And Louis de Broglie was awarded the Nobel Prize in Physics in 1929 for showing that electrons are both. Now I have a question again. Do we understand this wave-particle duality? Did the Nobel Committee understand what an electron is? I'm not sure they did. In fact, I'm not sure anybody understands it even today. So much so, in fact, that Peter Voigt, a mathematician from Canada, wrote a book that said, it's so far from making sense, it's not even wrong. Clearly, even scientists could use a little more analytic philosophy in their work. It would help them to make sense of what they're doing. What they do is fantastic. I don't want to downplay what scientists do, but I want to say they're doing it and it works and they're using it and they make the technology, but they don't really understand it. The understanding isn't there. The depth of understanding isn't there. So I think scientists could also benefit from a little more scientific literacy, or STEM. So scientific literacy is essential for scientists, but it's also essential for us non-scientists. It's essential for me. It not only enables us to understand the scientists, it helps us to better understand the world in which we live. And I think that's essential. Scientific literacy is more relevant and important than ever in our high-tech, industrial, technological age. I mean, just imagine if everyone was scientifically literate, there'd be no young earth creationists, there'd be no anti-vaxxers and no climate change deniers. It'd be heaven on earth. So I want to argue, I'll end on this note, I want to argue that STEM matters. I think it's important, but I don't think STEM is really just science, technology, engineering, and maths. I think science needs scientific literacy and vice versa. I think Einstein said that well when he said epistemology without contact with science is empty, and science without epistemology is primitive and muddled. I think these two have to work together. Science, technology, engineering, and maths are really just an odd collection of disciplines lumped together because they all have one thing in common. They have a requirement for deeper understanding of scientific principles and critical analytical thinking. And I think that's what sets STEM subjects apart from everything else that we can think about. STEM is not just science, technology, engineering, and maths. It's the study of the underlying foundational principles of the scientific method and of how things make sense. That's what I want to argue STEM is about, and that's why I think it matters. Knowing scientific facts is not the same as being scientifically literate. Memorizing is not the same as understanding. Learning science, technology, engineering, and maths is no substitute for being scientifically literate. Without STEM, you can do science, but you can't understand it. For that, we have to learn to think critically, perhaps clearly, logically, scientifically, or systemically, perhaps. And that is, I think, what STEM is for, and that's why it matters. STEM is universal. It applies to everything. And we all want answers to the big questions. We want to know where the universe came from. Was there a beginning? Is there a creator? What went bang? Where did we come from? What is consciousness? What is the meaning and purpose of it all? It's why we study cosmology and why many of us embrace religion. But again, these are mostly not scientific questions. They cannot be answered by doing STEM. To the extent that they are about the physical world, they are STEM questions. But beyond that, they are metaphysical, philosophical questions, And the answers to these questions will in fact direct us in our scientific inquiries. And not just any answer will do. I think we want to know what really happened. We want to know how things really are. We want to know what's really going on. We want plausible answers, things that we can understand, things that make sense. We want facts and not just stories. We're not going to be happy with stories like the Big Bang happened because some creator waved her magic wand and said abracadabra, and poof, there it was. Or even stories like Stephen Hawking's The Universe Created Itself from Nothing. In other words, it pulled itself into existence by its own bootstraps. He wrote that in The Grand Design. What does that mean? How do we make sense of that? These are not the answers we want. And STEM matters not only to people who work in the field, it matters to each of us, every single one. Everyone needs critical thinking, everyone needs scientific literacy, everyone needs a little mathematics and science. And then maybe some of us who go on to be scientists need more maths and more science, and plus you need some technology and engineering. But everybody needs the initial underlying critical thinking and scientific literacy. So maybe then STEM should be called something like CTLS-MS plus TE, critical thinking, scientific literacy, maths and science, plus technology and engineering. But CTSLMS plus TE, I doubt that acronym will catch on. So let's just call it STEM, but let's understand what STEM really is. So I think we should be rushing headlong into the age of CTSLMS plus TE as fast as we can, at 100 miles an hour, like the Flying Scotsman did in 1934. Let me add with some acknowledgements. This is my research team. Here are their names. And let me thank you for your attention.
Thank you, Tibor. Now, if people have got any questions, they could actually use the chat box to type their questions in. I have got 2 questions already, Tibor, which I'll relay to you to answer on behalf of the group.
Okay, thank you.
The first question is, what do you see, I know you've answered it throughout your presentation, what do you see as the most pressing challenge with students and educators in STEM education today?
I think the answer lies in the fact that scientific literacy is at record lows, or very near record lows. They were somewhat lower about 5 years or 10 years ago, but they haven't improved much. I think the most important thing for the world today, for students today, is that they come out of school, they come out of university, and they don't just have a whole lot of things that they've learned how to do, how to pour liquids from one test tube to the other, but they've also learned what it means. They need to understand the world. I think they need to be scientifically literate. That will give them a certain confidence, a certain comfort in their dealings with the world, because they'll know a little bit about what they're dealing with. And it will also mean that they will understand what the scientists are doing. They will accept the technology which is offered to them. They'll cope with it better. And I think the whole world will run much more smoothly if people are familiar with the science and the technology that surrounds them. So I think that's the mission statement. I think that's what we want to achieve. And I would argue that's already what we're trying to do, except that we may not be doing it as effectively as we can. I think everybody understands it. This is why STEM matters. We want people to be STEM literate. But maybe STEM literacy isn't just learning science and technology and doing experiments. Maybe there's a STEM course I once saw where they taught people to fly airplanes. Well, that's fine. That doesn't teach you how to be scientifically literate. It teaches you a little bit of science. So I think there's this underlying understanding of the world which we need to engender in our students. And I think that's the most important challenge facing us. I'm happy for feedback. If anyone's got a thought, if you want to argue with that and say, no, Tibor, you're all wrong, we need something else, then please go right ahead. But I think that's where we should be, that's what we should be aiming for. And I think that's the the end result, which if we achieve that, I think we've really achieved something.
And Tibor, the second question I received, technology has transformed many aspects of how students engage with STEM learning. What do you see as the greatest opportunity related to technology in STEM education?
Oh, that's a many-faceted question, I think. Yes, you're right. Students do engage with the technology. Maybe what we can do is ask them not just to use the technology, but somehow to understand why it works and how it works. Maybe they can make the technology themselves. They can build replicas of it. They can take it apart and find out how the bits work and get to understand the underlying science. I think there's a little bit of physics in every bit of technology. So there's a whole lot of science that we can teach by showing them the technology, sure. And they're going to say, oh, that's interesting. I want to use that. And then you can say, well, if you want to use it and play with it, then you have to understand how it works. And that gives you the opportunity to dig into how it works and why it works. So I think there's an opportunity in technology to drill down into the science and then drill down into the understanding of the physical realm through the interface of technology. I hope that addresses the question. I'm not quite sure that it does.
Is there any further questions from the audience? No? I've just got one more question, Tibor, that just came through.
Yep.
And this is probably a good question. How does one know when students are effectively engaged with what they're learning with STEM?
I think it's easier to know when they're not, because they're playing with their phones or they're staring out the window or they're spaced out in some way. I think their enthusiasm shows. I was at a lecture at New South Wales University where Pashi was giving a talk, and there was a video of students that were really engaged with some experiment they were playing with. They're really working out how something works. And you could tell they were engaged. They were as enthusiastic as anything. And they came in early and they went straight to fiddle with it and they wanted to play and they wanted to discover. I think if we set up something which involves the students discovering the world rather than us teaching it to them, then they will engage with the journey of discovery. They'll find that exciting. One of the problems with STEM is that you can't really teach it. What you can do is you can facilitate students to learn it. I think the learning happens the students have to do the learning. We can't do the learning for them. We can only do the teaching. And we can teach all we like. If the students are not engaged, they're not going to learn anything. So somehow what we have to do is set up an environment in which the students will engage with the environment and they will learn. So all we do is set up the environment. I think the learning comes from them. If the environment is attractive enough, they will get engaged. They will do it. They'll be curious. I don't think, excuse me, what we do in schools is we actually teach students not to be curious. I think it's really sad. When they're 8 years old or 10 years old, you can't get them. So still they're so curious. They want to know everything about everything. By the time they're 15, they don't give a damn. You've lost them. Something goes on between the ages of 8 and 10 and 15 where the education system teaches students to learn, to make notes, regurgitate what they've learned, pass the exam, and forget to think and forget to ask questions and forget to be curious. I think that's what we have to change. It has to happen maybe in late primary or early high school. We've got to maintain and nurture and foster the curiosity of students, and then that curiosity will make them engage. If we doing it in year 12 is too late. You've lost them already. I think the challenge is to get them curious, and then they will engage, and you'll see it. You'll know it. You won't be able to get them to sit still, and that's when you're achieving something.
Thank you. Tibor, you talked about critical thinking. A question just came through. Are there any tips you have for teaching critical thinking?
No, I don't, or at least not good ones. There's plenty of courses in logic and there's plenty of other courses in philosophy of science and so on, but they're typically not very good. I mean, I can blow my own trumpet here and I can say I teach a course in critical thinking and that's the best one you can do, but that would be cheating. There's very little available. And I recognize the problem. I think, and I don't want to denigrate the people in the room. I admire what you do as teachers. I don't think I could do it. But I wonder how skilled our teacher cohort is in critical thinking, in these things, because they weren't taught either. They went through school without it. They went through university. They learned how to teach, but they didn't learn critical thinking. And then you came out and somehow it's assumed that you're all critical thinkers. And in some ways you are, and in other ways you're not. You certainly have a lot of life experience that makes you good as human beings, but are you scientifically literate? Are you critical thinkers at the level at which I'm suggesting we need to be, and at the level at which I would like our next generation to grow up to be? And that's a challenge. I don't know the answer to that. You teachers have access to many more resources than I do. So hopefully you can disseminate information about these resources and maybe do something about becoming more critical thinking and more scientifically literate yourselves, just at least to learn the terminology, even if you already know what you're doing, which most of you, I'm sure you do, but if you just need the terminology to help you express it and help you explain things and help you get the message across to the students, even that would be an improvement. So I don't know the answer. I don't know where the resources are. They're bound to be out there. There's lots of interesting stuff on the internet. I haven't gone particularly looking for these resources, but I'm sure they're there. And if you find them, then please tell everybody and jump on it and learn and upskill yourselves so that you become better STEM educators. I can only encourage you to do it.
Thank you, Tibor. I can't see any questions coming through. This gives me an opportunity to thank you again on behalf of the Teachers Guild New South Wales for providing us engaging presentation on learning with STEM and what the world must be like. We appreciate your wisdom, your expertise, and for everyone, the recording of this presentation will be available after the event, and that will be sent out to everyone as a link. Thank you very much for joining us today, and we hope to see you at a future Teachers Guild New South Wales meeting. Thanks again.
Okay, and thank you, everyone.